जब तक तोड़ेंगे नहीं तब तक छोड़ेंगे.
Hello everyone, today in this video we are going to derive the electric field due to an infinitely long straight charged wire. So after this video you should be able to derive the expression for electric field. So for that we consider an infinitely long charged conductor. So suppose this is an infinitely long positively charged conductor. So in order to find the electric field, we consider a cylindrical Gaussian surface around this charged conductor. So here I have considered a cylindrical Gaussian surface around this conductor, and R is the radius of the cylinder and L is the length of the cylinder. So now we use Gauss law to find the electric field due to this infinitely long charged conductor. So now I can divide this cylinder into three parts. That is, one is this circular top part, and surface 2 is this circular bottom part, and the remaining body, that is curved surface area, is the third area for this cylinder. If we consider this cylinder, this part will be our one surface area, which is a circle, and out here we have another surface area, and remaining part, that is the curved surface area, will be the third surface. Now we will use Gauss law to calculate the strength of electric field due to this wire. So now this is the same picture which I have explained. So this is an infinitely long wire, and the charge density of this wire is lambda, and we are considering a Gaussian surface around it, and the shape of the Gaussian surface is cylinder, and the radius of this cylinder is R and length is L. And we know the line charge density is given by lambda is equal to charge by length, and for this cylinder, if Q is the charge, then lambda will be Q by L, and we can write Q is equal to lambda L. So this is the charge enclosed by this cylinder. So from here to here the charge of the wire is Q, that is lambda L. Now I will find the flux through this surface and the curved surface, and I'll add them up to find the total flux. Now we will divide the cylinder into three parts, S1, S2 and S3. So you can see this top part is S1, and this middle part is S2, and this bottom part is S3. Now for this surface S1, you can see the direction of electric field is away from the wire, and the area vector, which is the perpendicular to the surface area, is going upward. So you can see the angle between them is 90 degree. So I'll find the flux through this surface first. I'll consider the small area in each surface, that is in S1 I consider the small area ds1, in S2 I consider a small area ds2, and in third surface I consider an area ds3. And now for this area, the area vector is going upward and electric field is going in this direction, so angle between them is 90 degree. And now for this surface, the electric field is radially outward, and if you consider this area, the area vector that is perpendicular to this area will be in the direction of electric field. So out here theta is equal to 0 degree, and similarly you can see ds3 is in downward direction and E is in this direction. So here the angle is 90, so 90, 0 and 90. Now I will find the flux through this area and this area, and to get the total flux I'll add all three flux. Now for the surface area S1, that is the top part, we already know the formula for flux is equation of E ds cos theta, because in dot product we get cos theta, and for surface S1, ds1 and E are perpendicular, so theta is 90 degree, so I'll get this to be 0 because cos 90 is 0. So flux through the first surface is 0 because there is no electric field which is crossing this surface, because there is no electric field in upward direction, so there will be no flux. Now similarly for surface S3 also, direction of DS and E are perpendicular, so I can directly write phi 3 is equal to 0. This is for the bottom part of the cylinder, so the angle is 90 degree and cos 90 will be 0, so I can directly write this by saying similarly as the first case. So now for the second surface is this curved surface area of the cylinder, and for this part the direction of E and area vector is same. So for surface S2, flux will be given by this expression, E dot ds2 or E ds2 cos theta. So for this surface theta is equal to 0, so when I put theta is equal to 0, cos 0 will be 1 and I'll get E ds2, and this will be flux is equal to E integration of ds2. We have to find the integration of ds2. Out here this is ds2. If we add all the area like ds2 throughout this surface, then we get the curved surface area of the cylinder. So we have to add all the small area that makes the curved surface area of the cylinder. So integration of ds2 is the curved surface area of the cylinder, and curved surface area of the cylinder is 2 pi rl. So flux is equal to E into value of this ds2 integration will be 2 pi rl. Now the total flux will be flux 1 plus flux 2 plus flux 3. Flux 1 and flux 3 are 0, so flux 2 will be this much. So this is the total flux through the cylinder. So this is the total flux through the cylinder, and according to Gauss law we know flux is 1 by epsilon naught times the charge enclosed, and we have already found out the cylinder enclosed the charge of lambda L, where lambda is the line charge density. So phi is equal to lambda L by epsilon naught, and we know phi is 2 pi E 2 pi RL, and we know flux is E 2 pi RL. So if you put the value, L will get cancelled, so this part will come down, so electric field will be given by lambda by 2 pi epsilon naught R. So this is the electric field due to a charged wire, and it depends on the distance r from the wire, so it is inversely proportional. So if you go far away from the wire, the electric field decreases.
जब तक तोड़ेंगे नहीं तब तक छोड़ेंगे।